This is a recording for notes for section 1-6 in pre-calculus, and it is called a library of parent functions. So you want to take good notes on this. These are kind of the basic functions that we'll then manipulate and make transformations of, many of which are familiar to you, a few of which are less familiar to all of us because we just don't use them as much. A library of parent functions. And our objectives are to identify and graph linear and, oh, sorry about that. Oh, gosh. Linear and squaring functions. So those should be things that are familiar to us. Cubic, identify and graph cubic, square root, and reciprocal functions. And then identify and graph step and other piecewise defined functions, and recognize the graphs of parent functions. So this is just kind of an overview of all of these functions. So by the end, when we kind of revisit the objectives briefly, hopefully you'll have a good handle on all of these. So we'll start with the linear and squaring functions. We're probably the most familiar with those. And by all means, pause this as I go because I will just be running through each of these functions. So we want to be able to recognize basic shapes of the graphs of different types of functions. Kind of keep in mind, you know, we're not using a graphing calculator now, so we don't have that instantaneous picture, and we want to have a picture in our minds. So a linear function, f of x equals ax plus b, is a line. It has a slope of m equals a and a y-intercept of 0b. And so this is our first function, and we want to write, you know, kind of a lot of things about it. And I'm just going to start listing things off. It has a domain, D, which goes from negative infinity to positive infinity. And when and that is when it is a linear function. The only line that's not a function is a vertical line. And so this is looking at linear functions. And then if the range is also from negative infinity to infinity, except if m equals 0, or a equals 0, then we get y equals b, and then the range, because that's going to be just a horizontal line, that's going to be a horizontal line at whatever b is. B I'll put right there. And so then the range is just that value of b. So, you know, there is that little exception for the range as we look at that. And think about the x-intercept, and could you get the x-intercept? That's when y equals 0, and we're going to kind of generalize that. So we have f of x. Let me write that better. F of x equals ax plus b. So if I want the x-intercept, and I'm going to just use this general form, that's going to be when y is 0, so it's going to be 0 equals ax plus b. Think about solving that. We would subtract b from both sides and divide by a, so negative b over a is equal to x in this case. And remember, a was also the slope, so we could have written this f of x equals mx plus b. And again, 0 equals mx plus b. Subtract b, divide by m, negative b divided by m equals x. And so we can say that the x-intercept of a linear equation is negative b divided by m comma 0. And you know, you don't always have to remember that, but you know, it is another method because it's not that hard to find the x-intercept. And then maybe I should be changing colors a little bit. And we know that the y-intercept is 0b as we look at that. So x-intercept, y-intercept, and other just facts about this is that the if m is greater than 0, it is increasing from left to right. And if m is less than 0, it's decreasing from left to right. And we'll just kind of get rid of that a little bit. And then if m equals 0, we've already said that, but it will be constant. It's constant. So just some other just facts about a linear equation as we look at that. And then the next slide just kind of goes through those characteristics. I'll leave it on here, but we've kind of written everything that we need to for this. And then let's look at number 1. Number 1 says write the linear function for which f of 1 equals 3 and f of 4 equals 0. So f of 1 equals 3 and f of 4 equals 0, and we want to write a linear function. So they're telling us it's linear. So if you remember, this can be written as an ordered pair 1, 3. This can be written as an ordered pair 4, 0. I am going to go through a whole process, but I'll comment at the end, and maybe you're noticing this is the y-intercept, but it wouldn't necessarily have to be. So I'm going to find the slope m, which is 0 minus 3 over 4 minus 1, so negative 3 over 3, or negative 1. I'm going to use y minus y1 equals m parentheses x minus x1. And I am going to use this point. It doesn't really matter. Y equals, or y minus 0. I should better write it first. Y minus 0 equals m, which is negative 1 times x minus 4. And then y equals, when I distribute that, negative 1x, or negative x. Plus 4. And so there's the equation of the line. That means that the slope is m equals negative 1, and the y-intercept is 4. And so that gives us that 0.04, which we actually are already maybe had an idea about as we looked at that. So let's look now at the next kind of function as we go, and that is the constant function and the identity function. So they're all part of this linear scope of things, and so and this is two separate functions kind of listed here. The first one is going to be this constant function. I'm going to write about that on this page. We'll look at the identity function on the next slide, I think, as we go. So the constant function is f of x equals c, and the domain is all real numbers, so from negative infinity to infinity. And the range is just whatever that c value is. And we could put it in braces if we wanted, or a bracket. Either way would be fine. And it is a horizontal line. And I'm going to just cross that out because we don't care about that. And if you want to draw yourself a little picture of it, it looks like that. So there's the constant function. Not a lot of, earth-shattering stuff to say about that. And it's just a horizontal line. So if you have to pause this to write some things down, I do expect you to know what a constant function is. Then we'll use this slide to write about an identity function. So the identity function is f of x equals x. And so if you think of that in terms of y equals mx plus b, y equals mx plus b, m is 1 and b is 0. And so that's why this is the graph of that. So you could maybe draw that. So the y-intercept is 0, the slope is 1, and so you can see that there. Um, for this one, the domain is from negative infinity to infinity, all real numbers, and the range is also from negative infinity to infinity, all real numbers. And so that's the basic ideas behind a constant function as we look at that. And then that is manipulated to kind of give us a lot of linear functions as we look at transformations later on. So not a word you're as familiar with in terms of lines, this constant and identity function, but certainly something you've experienced in practice. The next one is the squaring function. And the squaring function is, so it's the squaring function. And that is that basic f of x equals x squared. I have a nice picture of it in a minute here, but you know that it is 1, 2, 3, 1, 2, 3, 3, 4, 5. And if we wanted to plot some points, it's at 0, 0, 1, 1, 2, 4, and then negative 1, 1, negative 2, 4, and it has that nice U-shaped graph that we are very familiar with. And that's kind of the basic squaring function. It has that U shape. The domain is the set of all real numbers, so from negative infinity to infinity. The range of the basic parent function, we're calling these, is if I think of walking along this, oops, just kidding. If I think of walking along this axis, I don't see it left or right, I step on it right there, so it includes 0. As I go up here, if I look left, it's over there. If I look right, it's over there. So and then as I go forever, since these both go forever, it will go to infinity. So the range for this one, let me kind of get rid of a bunch of dots that I have there. So the range is also, or not also, it's from 0, and it includes 0 to infinity. And that's of just this squaring function. So that's what we get. This is also an even function. It can be folded on the y-axis. The intercept is at 0, 0. It has a minimum, which is also at 0, 0. And how about what's happening to it in different intervals? As we go from negative infinity to positive infinity, from negative infinity to 0, it's decreasing. So we always say the x as we give that interval. And then as soon as we get to 0, then we go to positive infinity, and then it's going to be increasing again. So if we tell where it's increasing and decreasing, it's never constant. So it's increasing in the interval from negative infinity to 0. These intervals are given with parentheses as we go. And then it's, oh gosh, I did that wrong. It's actually increasing. I'll just fix that. It's increasing from 0 to infinity, and it was decreasing from negative infinity to 0. And so that's something we want to kind of keep in mind. We already said it was even, and so it's also symmetric with respect to the y-axis. Maybe I could have said that right there. Symmetric with respect to the y-axis. And it has that minimum, we've already said that, and I think that's kind of everything that we need to have about that. And you can look at this slide, and if you want to pause it and read through that, just make sure we've said everything. And then there's a second slide. You could read through that also and make sure that we've said everything for that. And they have a nice little graph of that as well. So there's another parent function that we'll be looking at. Then the next set, subheading here is cubic, square root, and reciprocal functions. You should be pretty familiar with these as well. And so if you need to pause it to write that subheading, you can. Otherwise, I'm going to move along here. And so I'd like to go through these kind of one at a time, and they do here as well. So the cubic function is f of x equals x to the third. And if I just kind of draw a little picture of it here for myself, it goes when x is 0, y is 0, when x is 1, y is 1, when x is 2, 2 to the third is 8, so that would be up here at 8. And then at -1, it'll be -1, and at -2, it'll be -8. And so you're familiar with that curve that kind of goes like this. So it has a domain of all real numbers. Domain goes from -infinity to infinity. It has a range of all real numbers from -infinity to infinity. This one is odd, and we'll also write then that it's symmetric with respect, symmetric, I'll say maybe and, symmetric with respect to the origin for this. The intercepts, y and x and y intercepts so it just has one intercept, and that's at 0, 0, because it just goes kind of right through that as we look at it. It is increasing all the time. If you go from -infinity to infinity and you walk along the x-axis here, as you're walking along, you're starting way down here, and oh, that kind of drifted. You're way down here, and then you slow here, and then you pick back up speed, but you're always increasing for the cubic function. Let me get rid of all that yellow. And oops. So we will say it is increasing, and we'll give the interval. Sometimes, people will say along its whole domain, but we'll just write the domain from -infinity to infinity. Those are the x values that we give for that. And it's symmetric with respect to the origin. We have a little sketch here, and the book authors, of course, always do a little nicer sketch probably than I do. And so that is the cubic function. Make sure you have good notes of what exactly the cubic function is. And I'm going to go on to the next slide, and there's just more of that information. Just check that we wrote everything down. And then the next one is the square root function. So I'm going to write square root function. And since it's a function, it's only the positive square root or principal square root. So we'll say f of x equals the square root of x. And if we graph this, and I will make 1, 2, 3, oh gosh, I'll maybe just do a little better there. Oh, square root of x. And I am just sketching it. I should have maybe had you do it on graph paper, but 1, 2, 3, 4. We're committed now. 1, 2, 3. And so if I plot some points here, if x is 0, the square root is 0. If x is 1, the square root is 1. And then I'm not going to do 2 and 3 because those are not perfect squares, but the square root of 4 is 2. So that gives me another nice little point to have there. And if I try to use -1, I get I, so that's undefined. So this one kind of looks like that as we go. So a little bit different in some of our points that we're going to make about it. So for this one, the domain, if I walk along this x-axis, there's nothing up or down, nothing, 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 nothing. I step on it, so it's defined at 0, and then as I'm walking along, I look up and it's there, and that will happen as I go to infinity. So the domain for this one is 0, including 0. I don't know why I'm writing in red. Let me go back to green in a second. 0, including 0 to infinity. And likewise, range, same thing. So we're walking up here, nothing to the left, nothing to the right. We step on it, we can see it. You know, when I'm here, it's like way out to the right, but it is there. So I do know that it's there. And so the range is also from 0 to infinity, including 0, as we look at that. And both of those can also be thought of, as non-negative real numbers. Just another, way of talking about that for either one of those as we look at it. The intercept, x and y intercept, is the same thing. So intercept, just one, is 0, 0. And it is always increasing over its domain, so increasing from 0, 0 to infinity, and those intervals don't use that, so 0 to infinity. And so that it's not symmetric with respect to anything because it it can't. It's a function, so it can't wrap over the x-axis. It doesn't wrap over the y-axis, and we can't turn it like that either. So it doesn't have that, and it's not considered even or odd as we go either. So just read through that. Also, make sure you write good notes about it. Here's the nice picture of that, and we do want to have in our heads kind of a sense of where some key points are that we can plot for that. And then the last of this little subsection is the reciprocal function. So the reciprocal function, sorry. And so for that, that's f of x equals 1 over x. And if I graph that, if I put in 0, it's undefined, so it's going to have an asymptote there, and maybe you remember that, and if not, we'll kind of talk about it a little more. And then I know when x is 1, 1 over 1 is 1, so let me go back and put on. And so when I plot some points here, if x is 1, y is 1, so it's going to be right there. If x is like 3, 1, 2, 3, y is 1/3, so it's kind of really close there already. If x is 1/3, y would be 3, so we'd get that. If x is -1, y is -1. Same thing, if x is -3, this is -1/3. I can't even get that close. If x is -1/3, y is -3, and I get this picture. And it never touches the x-axis or the y-axis, and so try to draw a good picture of those for yourself so that you have excellent information there. So as I walk along here from -infinity to infinity for the domain, it's hugging, kind of almost touching, but not quite, that x-axis. Think about x being like -1,000,000, y is -1 over 1,000,000, so it's like super close. So I do see it from -infinity all the way to here. When I step right there, I look up and I look down and I see nothing. It's undefined right there. And then I start to see it again above me as I walk the kind of rest of the way, we'll say. So the domain for the reciprocal function is from negative infinity to 0, not including 0, union with 0 to infinity. Exact same thing happens for the range, negative infinity to 0, union with 0 to infinity. Um, and this one is odd because it has symmetry about the origin, symmetric with respect to the origin. So this one is odd, and it is symmetric with respect to the origin. So it kind of has that turn symmetry. It has no intercepts, no x-intercept, no y-intercept, so no intercepts. And uniquely, it is decreasing over its whole domain. So think about, that negative a million there. It's decreasing ever so slightly and then very sharply. It's undefined there. I don't have that in there very well. And then it hops up to kind of positive infinity, and it's still decreasing, 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 and ever so slowly as it goes out that way. So it is decreasing from negative infinity to 0, union with 0 to infinity. So over its whole domain, it is decreasing as we go. Excuse me. Other kind of just little points another little point we want to say here is, and they're not talking about it here, but it has asymptotes. Asymptotes. And asymptotes, if you remember from previous work, are where the function, a value for y that the function gets very close to but never actually achieves. And this has two asymptotes. One asymptote is the vertical line. I maybe, well, yeah, I'll have to freehand that. The vertical line at x equals 0, and then it also has an asymptote that's going to go that way, and I have it poorly drawn, but y equals 0 as well. So it has two asymptotes. Those are values that it gets very close to, but never actually hits. And I'll tell you something about this book author that's maybe different than other books you've had, and that is, do you see how the asymptotes aren't drawn in here? And maybe it's just the publisher or whatever, I'm not sure. But the asymptotes um, should, when they're on the axis, they do not appear in this textbook. So I'm just kind of letting you know that the asymptotes do not appear if they're on the axes, like drawn in, but they are there. So do be careful of that and know that as well. Okay, our last subheading is step and piecewise defined functions. And so step and piecewise defined functions, probably, people tend to be the least familiar with them and, so possibly like them the least or whatever. But but we will forge ahead. And they're not as bad as sometimes people think. So the step functions, and the most famous step function is kind of the greatest integer function. And we're probably a little familiar with that, maybe not the notation as much, but step functions. And so it's a sub one, and it's called the greatest integer function. And it is denoted kind of by this double bracket with an x inside. Oh, f of x equals, and that is defined as the greatest integer, less than or equal to, x. So it's sort of more intuitive or obvious when the values are positive versus when the values are negative, just to kind of let you know as we go here. And so I am going to use these two slides. So some of the values, so if we have the greatest integer of -1, that would be -1. The greatest integer of -1/2. And so for a greatest integer function, you know, if you want to just kind of draw a little number line here so you can kind of look at it, -2, -1, oops, 0, 1, 2, 3, 4, 5. So, you know, if it's at 3.5, we know the greatest integer is 3. But if it's at -1/2, right here, the greatest integer is actually the previous one, which is -1. So it's backwards like things often are with negatives as we look at it. So same thing here, and I'm just going to use a number line again, 1, 2, 3, 4, 5, 6, 7, 8. -3, -2, -1, 0, 1, 2, 3, 4. So if I'm at 1/10, which is like barely there, the greatest integer is 0. So it's the previous greatest integer. If I'm at 1.5, the greatest integer was 1. If I'm at 1.9, the greatest integer is also 1. So that's what we kind of have to think about. And I'm just using a number line. I'm not right now graphing the greatest integer function, but now we'll graph it as well. And so when we graph the greatest integer function, 1, 2, 3, 4, 1, 2, 3, 4. So what happens here is for this, if x equals 0, the greatest integer is 0. And all these decimals up to 1, but as soon as you get to 1, it hops back up to 1 here. And then all these, the greatest integer is 1 until you get to 2. Then you get to hop up here to 2. And it is still a function because it's going to pass the vertical line test because it's either going to be 1 here or, and I don't have that quite over there. I'll just kind of make it a little bigger. And then it goes to here, open circle at 3, but then at 3 it hops up to 3 over again and so on. And likewise back here, so all of these values will be the greatest integer, and maybe I'll go -1, -2, negative. No, I'll just go -1. I'm going to go this way. So at -1, it's going to be -1. And all these negative fractions are still -1 is the greatest integer. And then once we get to 0, it hops up there. And then same thing here. -2, it's -2. And then this way, -3, it's -3, and then to here, -4, it's -4, and then to here before it hops up. So the domain is actually all real numbers because as you walk along here from -infinity, like, you know, it's right there and then it's there and there and then it just keeps hopping up, but it's always visible from that x-axis if you're walking along that. So for this, the domain is all real numbers from -infinity to +infinity, but the range is a little bit different. The range is all of these integers as we look at it. And so the range, I'm going to give a descriptive range, is the set of all integers. Set of all integers. I can't write that as an interval. I could maybe write it in set builder notation, but if I'm walking from -infinity here on the y-axis to +infinity, notice this, when I step on, I think that's -4, I see it over there, but then I don't see it, don't see it, don't see it. I step here, I see it over there. I step here, I see it. I step here, I see it out that way. I step here, I'm stepping on it, and I see it. I step here, I see it, but only at those integer values. So that's something unique also about the step function. And then what else do we want to say about that? Um, oh, it has a y-intercept, so its y-intercept is right there at 0. So let me get rid of that. The y-intercept is at 0, 0. And it has x-intercepts. There's a whole interval of them right there. And so the x-intercepts are along the interval from 0, including 0, to 1, but not including 1. And so the other thing about is it increasing, decreasing, or whatever, it kind of has two dynamics here. In each of these little intervals, it is constant, but then it hops up uh, for the next interval. So it is constant. The way we'll just say that is constant between pairs of consecutive oops, integers. Integer values of x. So that we'll say that, and then we'll also add that it vertically jumps 1 unit uh, at each interval value, at each integer, integer value. So it kind of has that constant behavior and kind of that jumping. And I just said it jumps, and it's not continuous, and we haven't had that yet, but we will. And so it does have that characteristic as well. Kind of moving on, here you can kind of read all that. I think we have most of that. And then the next thing it does is kind of jump to a problem, and I'm gonna just go back a second, and this is about step and piecewise defined function. There's no parent of the piecewise functions, but they commented on it in the heading here, and so we do want to say something about it, and so I'm going to add it right after the step function. And maybe I'm going to just put a little empty here, and um, I'll put that piecewise. Since this one is a step function, we'll kind of look at it. So now they've put for number 2, we have to evaluate the function when x equals -1, 2, and positive 3/2. So we know what that step function looks like, but this one is a little transformation of that. So we have f of x equals the greatest integer of x plus 1. So if we will just put these values in as we go, and so f of -1 is the greatest integer of -1 plus 1. And so the greatest integer of -1 is -1 plus 1. So that's 0. And then f of 2 is the next one. So we want the greatest integer of 2, and then we're adding 1. So the greatest integer of 2 is 2, and then plus 1 is 3. And probably the hardest one here, because it's a fraction, is the f of 3/2. And so that is going to be the greatest integer of 3/2 plus 1. So 3/2 is 1.5, and the greatest integer there is just 1. So that's 1 plus 1, or 2. And so there are three solutions that were given for that one. And then I did have on here, this is the graph for this greatest integer function. Notice everything's just hiked up one as we go. So the piecewise function concept doesn't really have a parent function, but I want to put one on here just to kind of give us a little heads up, because that tends to be something that we're not always real familiar with. So a piecewise function, and this is just an example because there's no exact parent function of that. And so we're just going to have an example. It's going to be f of x equals, and it's going to have two pieces, negative a half, negative 1/2 x minus 6 for x that is less than or equal to negative 4, and x plus 5 is greater than, um, oh, and x plus 5, I didn't write that, when x is greater than negative 4. Couldn't read my own writing. Wow. And so, my advice to you sometimes is, when in doubt, plot it out. And so if we need to graph this, I maybe will get a piece of graph paper for this one. Oops, let me find my graph paper I should have here. And I think we'll graph, oops, this piecewise function. Let me get rid of that little thing there. So, we can kind of pretend, I guess, for this first part that we're just looking at this. The slope is negative 1/2. The y-intercept is negative 6. But we're just going to use points that are less than or equal to negative 4. So if I have some points that are less than or equal to negative 4, so I'm going to go negative 4, maybe negative 5, negative 6, that'll be a good value. Then f of x, the rule I have to look at is this one for less than or equal to negative 4, so it'll be negative a half times negative 4 minus 6, and so that is 2 minus 6, which is negative 4, and then negative a half, same rule because I'm less than negative 4, negative a half times negative 5 minus 6, and then that is 2.5 minus 6, so 6 minus 2 is 4, 3.5, negative 3.5, and then negative a half times negative 6 minus 6, that'll be 3 minus 6, which is negative 3. So I'll just plot a couple of those at negative 6. 1, 2, 3, 4, 5, 6. I'm at negative 3. I'll put the little dot there. At negative 5, I'm at negative 3.5. 3.5. And at negative 4, I'm at negative 4. So it's right there. And so that negative 4 is a boundary point. So I'm gonna actually darken it in a little bit because it's an end point, so to speak. And then the graph goes, let's see, from there. It kind of goes through there and out that way. And then I can put my arrow like that. So that's that piece of the function. Then the other piece, and I can kind of keep going, this is all f of x, but I will kind of change colors just so that you can see. So now I'm going to do some things in this interval from negative 4. And the deal is I'm going to maybe find what the value would be negative 4. This is going to be an open circle because it's not going to be equal there using x plus 5. And so negative 4 plus 5 is 1. And so this point, -4 comma 1, is not included, but it's like an end point, not included. So, and then I'll find some points that are greater than -4, so maybe -3. I'm not gonna use odd numbers because I get fractions. So maybe I'll go -2, I'll go 0, and I'll go 2. So let's see what we get there as we go. And now I'm using this rule because I'm using numbers that are values of x that are greater than -4. I'm going to use this x plus 5. So so I don't even have fractions. Oops. -2 plus 5, which is 3. 0 plus 5, which is 5. 2 plus 5, which is 7. And so I'm going to plot on here that -4, -4, 1, and that's going to be an open circle. And then I'm going to plot -2, 3, 0, 5, and 2, 7. And then I'm going to draw that in. And I'm putting it in red now, but I'm kind of going to draw over it in green because I do, or maybe I'll use black or something. Oops. Because I do want to think to myself that this is all the same function, and so I do want to have that kind of put in as all the same thing. So then what I'm going to do for myself is I'm just going to go to black and just a little thicker, and I'm going to say, okay, then the final result is that I would get this. And let me go to the black pen and make that a little thicker as well. And I can go like this, like this. If I wanted to kind of make that a dot, but this is an open circle, that's really the graph of this piecewise function. So just kind of a little bit of experience with the piecewise function as we go. And then the next couple of slides just are kind of that overview of just here are the parent functions. So this subheading is parent functions. We should have gone over all the parent functions, and so I'll show it to you and tell you to pause it if you want to see it more, and it will be on the PDF as well. So here are the parent functions. The 8 graphs shown below represent the most commonly used functions in algebra. A, the constant function, B, the identity function, C, the absolute value function. By the way, we did not do anything with the absolute value function, so you might want to pause that and add the absolute value function. Oops, because it wasn't on one of our other ones. D, the square root function. So pause this if you want to look at that further. And then E, the quadratic function. F, the cubic function, G, the reciprocal function, and H, the greatest integer function. And I'll just read what it says there. Familiarity with the basic characteristics of these simple graphs will help you analyze the shapes of more complicated graphs, in particular graphs obtained from these by rigid and non-rigid transformations. And when we move on, that's going to be kind of our next section is kind of transformations. So you want to have a good handle on these as you go. If you want to pause this and look at it, go ahead. Otherwise, I'm moving to the very last slide here. And oops, we want to make sure that we have kind of gone through this. So we should have be able to identify and graph linear and squaring functions, identify and graph cubic, square root, and reciprocal functions, identify and graph step and other piecewise defunctions functions, and recognize the graphs of parent functions. So that concludes the notes for 1-6. Have a great rest of your day.